And by the way, everybody just come down here and set this thing to say 200 per page, because if you're toggling the next page thing, you can get to a point where it's not even showing you anything in the drop box, and you just have to kill the browser and come back. So just set that to 200 per page. And here I set it to 20, not my goal. Alrighty, so what we're going to talk about today is binary and hexadecimal. Binary is the counting system that computers use. Binary means that the numbers are all zeros and ones, binary meaning 2. Okay. So we're going to talk about how zeros and ones form larger numbers, because we don't think of things as being zeros and ones. If we're going to store the year 2017, we don't think of zeros and ones adding up to 2017, but they actually do. So there's a worksheet in here, but I'm just going to lecture without the use of the worksheet for a while. So say we're driving in our car, and it's a weird car, maybe a Model T or something, that's got an odometer with only 3 digits in it. Heck, it's only got 2 digits in it. The car's not designed to go more than 99 miles. So we're driving along, we drive a mile, we drive another mile, we drive another mile, we drive another mile. Then what happens? We get to the 9th mile, we go another mile, and what happens on our odometer? And this isn't really a trick question, but I'm going to get into it in more detail. So what does it change to? Come on, y'all. You've driven cars. You know how odometers work. It goes to 10, right? Okay. So what does it really do? Our counting system is known as base 10, otherwise known as hexadecimal. And if we want to get really nerdy mathematical about it, we're going to say that this is a radix 10 math system. Okay, forget that. I'm deleting that. I don't care about that. And it's not hexadecimal. Where did that come from? It's decimal, right? Like a decade is 10 years. Decimal means 10 digits. So we have 10 digits. Now if you ask somebody for the 10 digits, they might go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But a 10 is really a 1 and a 0. So our digits actually start with 0. And until the invention of the 0, then math was kind of limited. It wasn't very easy to do multiplication or division like Roman numbers. What is MC times VII? I don't know, but it's easy, right? Using our Arabic numeral system right there. So what's happening is this number is going up through our numbering system. It goes from a 0 and it clicks to a 1, a 2, a 3, 4, 5, 6, 7, 8, 9. Once it hits 9, it doesn't have any more digits in the numbering system. So it flips back to being a 0. But then we carry a 1 over to the next column, and we increment the next column. And we've done this since the first grade, so we know how it works in our head. But that's really what happens, is we hit the 9, we've maxed out our digits, so we reset it back to the first digit and add 1 to the next column. Did we keep cruising down the road? We're driving faster now. Here we've maxed out our counting system again, right? We've hit 9. There's no more digits after 9. So we reset it back to 0, and we carry the 1 into the next place. We increment this one by another one. And so we keep cruising all the way down, and we're finally at 999. That one's maxed out, so it flips to being a 0, and we take 1 and we increment that one by it. But that one's also maxed out. So that one flips to being a 0, and then we carry the 1 and we add it to the next column. Now there's an implied 0 here, so it becomes 100. Or if it's a car odometer that really only has 2 digits, then we're stuck with 00, and it starts counting again. Back when you had an old-fashioned car with only 5 digits on it, and it was really exciting when you hit 100,000 and it wrapped around. Woo, I had all zeros there for a moment. So that's the way our counting system works. Is we keep adding 1 to the column until we've hit the largest digit that it can support, and then we reset it back to 0, and we go to the next one. Now let's say we had a strange counting system, and we're never going to talk about this one again, where there's only 4 digits. And so we hop into our car that counts only in 4s. You know, maybe we are rabbits, and instead of counting on 10 fingers, they just count 1 per paw. That's stupid. But anyways, so you're going along. This is what's known as base 4, because we only have 4 digits in it. We got a 0 and a 1 and a 2 and a 3. No other digits. Just like our base 10 went all the way out to 9, because that's 10 digits if you include 0. Base 4 goes out to 0, 1, 2, and 3. Okay, so our rabbit car is going along. We've maxed out this column. What's the next mile?
10.
Yeah, it's 10, because we reset this one and we carry the 1 over. And so later on, we're at 33. We go 1 more mile. That one resets back to 0. There's something funny going on. I guess it's not a monospace font. Just a second. That looks better. So that one resets to 0. The next one increments by 1, but, well, it's maxed itself out too. And so the next, that imaginary 0 there gets incremented to 1. So that's how our counting systems work. And we don't think of it in those terms because, we've learned this stuff so long ago that we know it like the back of our hands. Probably a lot better than we know the back of our hands. That's a silly expression. How well do I really know the back of my hand? Do I sit there and examine it a lot? Well, maybe more than I should, because I kind of think the veins moving around is funny. But anyways, so that's base 4, and I'm going to delete that because nothing ever uses base 4. For a while, computer scientists used something called octal. Octal meaning 8, so guess what the digits were? Where would octals stop at? We have 8 digits, so starting at 0, we would count up to.
7.
We would count from, 0, 1, 2, 3, 4, 5, 6, 7. We're not going to talk about octal. Binary. We only have 2 digits, 0 and 1. So counting in this looks a little bit weird. Go 1 mile. Go another mile. Well, we've already maxed out our system here, so that one flips to being a 0, and we add 1 to the next column. We go another mile. We've already hit our freaky condition where we've maxed out 2 columns now. So this one flips to being a 0, and we add a 1 to that. But this one is already maxed out, so it flips to being a 0, and we add a 1 to the next column. And there we go. Like that. That's how you count in binary. And we could keep going. I think I've messed this up. There should be 8 different digits. Do I have those? 1, 2, 3, 4, 5, 6, 7, 8? Yep, I have them all right. Okay. So if we look at it, if we only have 1 bit, a bit is a place in computer memory that can either be on or off. It either has some electrons in it indicating that it's on, or it doesn't have any electricity in it, meaning that it's off. If you only have 1 bit, you have 2 possible values. If you have 2 bits, 0, 0, 0, 1, 1, 0, 1, 1, you have 4 possible values. You have 3 bits. Am I going to count those again? No, I'm just going to copy and paste. You have 4 possible values. 8. We just counted those. So think back to computers a long time ago, 70s, 60s, whatever. They had black and white screens, right? Maybe they put, green on them so that they were green and black rather than white and black. But they only had 2 possible colors on them. So even if they drew a picture, it was just black and white, or black and green, or whatever color that they happened to color, Then, so even the first Macintosh, 1984 or whatever, it was a black and white screen, even though it was kind of a nice sophisticated thing where you could drag windows and stuff around. Still black and white. You could upgrade the video in some of these old computers so that it supported various shades of gray. And that you can make a lot better picture, right? Not a great picture if it's only got 4 shades of gray, but still a lot better than only being black and white. There is a relationship between how many bits you have and the number of possible values you have. It's actually a mathematical relationship. 2 to the power of n, where n is the number of bits you can dedicate it to it. So 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. So I don't know if any of y'all are old enough to have ever had a video card that only supported 16 different colors. I think it was called CGA or something like that. But that's because they were 4-bit values. I'm not going to count all the 4-bit numbers. You already know how to do that now. But from 000 to 111, you have 16 different values. If you have 8 bits, 000000000 all the way to all ones, you have 256 different values. So you think maybe you had a Nintendo when you were a kid, you know, or the Game Boys, I guess, were black and white, but maybe they had shades of gray too. But you had your Nintendo with the original Mario on it. Its screen was limited to the number of colors it could display on the screen at the same time. Maybe it could only display 16 different colors on the screen at the same time. I don't remember. But it probably had a color palette to where those 16 colors that it could keep on the screen at any one time were chosen from 256 different colors. So that's an 8-bit. You could buy a 8-bit video card for your PC that would display 255 different colors. And that was kind of, ooh, this is getting pretty. I'm not just playing in 16 colors. But then you could get a better video card. So that instead of 8 bits per color, you have your 16-bit per color. That's 65536. Yep, he sat through this before. Values. That's like your Super Nintendo or your Genesis. Your Nintendo had 8-bit graphics, and then the Genesis came out and they were bragging about how much better their graphics are. They had, they could display much better pictures on the screen. So the Super NES came out and competed with them. I'm not going to type out 16 zeros and 16 ones, but you get the idea. And then the PlayStations came out where they had 32 bits. All right, so I don't have these values memorized anymore, but we can calculate it pretty easily, right? 2 to the power of n. Google is my buddy. 2 to the power of 32. That's a lot of colors. That's why you could display, just about photorealistic stuff using 32 bits. So for a while, graphic systems on PCs and on Macs did support 16 bits, and so you could have any one of 65536 colors on the screen, which wasn't photorealistic. It looked nice, and you could have nice looking games, but you couldn't do photo editing on them. It wasn't until video cards got past that, 24 bits or 32 bits, that you had enough colors, represented that you could, have photorealistic. There may be a slight exaggeration involved there, but anyways, so 32 bits. That's why your PlayStation looks so dang better than your Genesis and your Super Nintendo, because the color palette was so much larger. Is the eye even capable of discerning more than 42 billion or however many? Let's add some zeros here just to see what this looks like. 4 billion different colors. No. Doesn't. Okay, so graphics are one place where the increased number of values played a role. But then more recently, you probably had the difference between 32-bit Windows and 64-bit Windows. And Apple's iOS is going through the same thing, where their applications were all 32-bit applications, and then they upgraded the chips to support 64-bit applications. And the next version of iOS is going to kill off all the versions of the programs that run in 32 bits, which I think is rude, because there's a lot of games and stuff like that that have never been recompiled. You know, maybe they will once the operating system comes out and they stop getting any money. But anyways, so why does it matter whether you have a 32-bit application or a 64-bit application? The bits also determine the amount of RAM the thing can access. If you think back to the early PCs, you could not install an 8 GB chip in it, you know, and have, you know, your IBM PC or your PC Junior or whatever, you know, was available in 1983, access 8 GB of RAM. You were lucky if you could get access 1 megabyte of RAM. Bill Gates said that no computer will ever need more than 640 kilobytes. Well, nowadays every machine comes with gigabytes upon gigabytes of RAM installed on them. It's not because Bill Gates was dumb. He just said that. He's an extraordinarily smart guy. So, where was I going with that? The maximum amount of RAM that the 32-bit Intel chips could access with a 32-bit operating system installed on them was 4 billion bytes. Maybe you could hack it to do something more, but you'd buy a computer and your laptop would probably have a maximum of 4 gigabytes in it after a certain point. You know, before that it was less. But if you had Intel chips that supported 64 bits and you installed 64-bit Windows, then you could access much larger amounts of RAM. You were no longer limited to 4 gigabytes. You know, so nowadays people buy things with 8 gigabytes or 16 gigabytes or whatever. And we're using these terms mega and giga and stuff like that. You've probably heard of kilo and kilobytes and megabytes and gigabytes. And if you've taken a science class, physics or chemistry, you've probably heard of, you know, milligrams, and I don't know when you ever used giga.
Gigawatt.
Yeah, gigawatts, and, you know, the time machine, you know, needed 88.4 gigawatts in order to go back in time or whatever, you know. And then, you know, megabyte. No, I didn't want to use RAM, but anyways. So, kilo in the science world means 1,000. A mega in the science world means 1,000,000. How about I just type out? No, I'm going to go ahead and type out the numbers. And then a gigawatts, as they pronounced it in there, is 1 billion. So these are Greek prefixes. You could have kilograms, where the kilo comes from. It's 1,000 grams. You could have a megagram. Do people talk about megagrams? No, but it would mean 1,000,000 grams. And a gigagram would be 1 billion. Now, computer scientists define kilo, mega, and giga slightly differently. They do it in powers of 2. And there is no power of 2 that adds up to 1,000. Instead, a kilo to a computer scientist is 1024. And a mega to a computer scientist is well, that's not right. That's a lie. Okay. That's the right one. And a gigabyte. Again, it's a little bit off, you know, but it's close enough that they use the same Greek prefixes that they borrowed from, you know, from the scientific world. And, you know, it's 1 point whatever billion, you know. So a lot of manufacturers of hard drives and RAM and stuff like, well, hard drives in particular, would advertise that they have a, you know, a 16 megabyte hard drive, and then when you actually formatted it and stuff like that, it had less than 16 megabytes as far as your computer was concerned. And that's because they just took the number of bytes and then they divided it by 1,000,000, whereas a computer thinks of it as in that term. But anyways, so that's where kilo, mega, and giga comes from. You know, kilo is about 1,000, a mega is about 1,000,000, and a giga is about a billion. So nowadays when you buy your computer and it runs at 2.4 gigahertz or whatever, it's running 2.4 billion instructions per second. It's amazingly fast. Just computers are amazingly fast anymore. And then there's another one, terabytes. You may have bought a terabyte drive recently. That's a trillion. I'm not going to type all those zeros. All right, so back to bits. Where was I going to go with this? I better look at my worksheet to see where I was going with this. So converting from binary to decimal. Yes, sir.
Are we supposed to make a program that does that for us?
No. You can, but no, we're not going to write a program that does it.
All right.
Okay, if you've already done it, that's really impressive. But no, you don't have to do that. There is a way that you can convert from one to the other. Okay, so say we have a binary number. First off, let's say that we have the number 982 in decimal, in base 10. What does that really mean? That means 9 times 10 to the power of 3, because this is the third place, plus 8 times 10 to the power of 2, plus 2 times 10 to the power of, no, that's wrong. It's like that. 10 to the power of 2, 10 to the power of 1, 10 to the power of 0. So in grade school we learned that that's the ones place, that's the tens place, and that's the hundreds place. Why? Because 10 to the power of 2 is what? Yeah, and what's 10 to the power of 1? It's 10. And 10 to the power of 0, well, that's a slightly stranger thing, but any number to the power of 0 is equal to 1, for a reason that I could get on the whiteboard and draw, but it's not really important. So this is the ones place, this is the tens place, and this is the hundreds place. So 900, because 9 times that, so we could say that this is equal to 900 plus 8 times 10 to the 1, 80, plus 2, right? And then we add those back and we get 982. All right, big deal. We converted from 982 to 982, but that's because we stayed in the same base. So if we have 10 to the power of 2 in that place, and we have 10 to the power of 1 in that place, and we have 10 to the power of 0 in that place, and that's how 987, I'm putting spaces now to make it real clear. If you have binary numbers, you have 2 to the power of 2, and you have 2 to the power of 1, and you have 2 to the power of 0. So we already said that 10 to the power of 2 that makes that the hundredths column, and then 10 to the power of 1 is the tenths column, and that's the ones column. So what is 2 to the power of 2? 4. And then what's 2 to the power of 1? And then what's 2 to the power of 0? Well, there we go. So if we have the number 1, let's just go whole hog and max it out. 111, that means 1 times 4 plus 1 times 2 plus 1 times 1. Or if we wanted to write it out longhand, 1 times, 2 to the power of 2, that gets tedious, plus 1 times 2 to the power of 1 plus 1 times 2 to the power of 0. Come on. You can see why I don't like referring to it like that. But okay, so what's a 4 plus a 2 plus a 1? 7, right? So a 111 in binary is a 7. So if we start at 0, that's the same thing as 0 times 4 plus 0 times 2 plus 0 times 1. Okay, you add all those up, what do you get? Yeah. So here we don't have any 4s. We don't have any 2s. How many 1s do we have? 1. Okay. So we got 1. Do we have any 4s here? Do we have any 2s in it? Do we have any 1s in it? Nope. So that's a 2. And so on. All the way down to 11111, which was 4 plus 2 plus 1. So if you're going to use more bits than 3, you have the 1s place, right? You have the 2s place, you have the 4s place. Guess what the next one is? 8. And then you have the 16th place, because 2 to the 0 is that, 2 to the 1 is that, 2 squared is that, 2 cubed is that, 2 to the 4th is that. Guess what? 32, 64, and lastly 128. Okay, I've gone out to 8. 8 bits is a very common thing. Computer engineers, designers, and programmers all love these powers of 2. So 8 is a power of 2, so 8 bits made sense to them. Now anyways, so if you have this number, 0, I'm just going to type in 0001, 0111, that's 8 bits. I'm going to wrap them out like this. 0, 0, 0, 1, 0, 1, 1, 1. And then now I'm going to add them together. Do we have any 128s? No, we don't have any 64s either. We don't have any 32s, but we have a 16. So that is 16 plus no 8s. Do we have any 4s? Yeah, we have a 2 and we have a 1. So 16 plus 4 plus 2 plus 1 is equal to 23 if I have done my math right. Let's completely max it out. 8 1s. I'm going to copy that again. So we have a 1 there, 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 and a 1 there, and a 1 there. That's the whole shebang, right? That's 1 times 2 to the power of 8 plus, excuse me, to the 7th, because we're going to go all the way down to 0, plus 2 to the 6, plus 2 to the 5, plus 2 to the 4, plus 2 to the 3, plus 2 to the 2, plus, and this will be the last time I ever do this, this class, plus 2 to the 0. So in other words, it's a 128 plus a 64 plus a 32 plus a 16 plus a 8 plus a 4 plus a 2 plus a 1. Now, do we have any math gurus who already know what that is? You probably don't. Yeah, you could whip out a calculator, but it's 255. So that means that from 00000, okay, 8 bits, like that, all the way out to 111111, the smallest numbers that it can hold is a 0, and the largest number is a 255. How many of y'all have ever had to like type in an IP address into a computer? What's an IP address? How many numbers is it? Is it 3 followed by 3 numbers separated by periods, or 4 numbers separated by periods? I think it's 4, like 192.6.3.1 is, I think that's right. So anyways, those numbers in an IP address, each one of those can be from 0 up to 255. And now you kind of see why. That's an 8-bit, that's an 8-bit, that's an 8-bit, and that's an 8-bit. So that's 32 bits devoted to your IP addresses. And the world's running out. This is what's known as IP4, Internet Protocol 4. The world's running out of different IP addresses. In fact, it's almost pretty much maxed out in routers, and the big companies that carry the vast amount of traffic, the internet backbones, do all sorts of tricks because we've already maxed out pretty much the maximum number of IP addresses, which you could figure out is 200 that times that times that times that. That give you the number of IP addresses. So IPv6 has 64 bits rather than 32 bits devoted to IP addresses. And so eventually everybody's Ethernet cards and stuff like that are going to have to support 64-bit addresses rather than 32-bit addresses. Trying to get you to the idea that of some stuff that you may have seen already in the past. And a lot of y'all have typed in IP addresses. You go into your network settings and you reconfigure your IP address for this reason or the other. And the reason why there's 4 of them and the reason why the numbers go up from 0 to 255 is because, so a number that's got 8 bits in it is equal to a byte. Okay, now I'm going to say this word, but don't ever answer it in any test question. So what did they decide a half a byte was? It's just a nibble. There really were people who called 4-bit numbers nibbles. So back in the old days, if you had your Commodore 64 or your Apple or whatever, and you were going to write a program that would copy one disk to another, you might call it a nibbler, because it was reading 4 bits at a time and writing it to the other disk drive, whatever. So 8 bits is equal to 1 byte. So this is a 4-byte address right here. Am I going to ask you on the exam how many bytes an IP address has? No, but I'm going to ask you how many bits are in a byte. So why is the bit the minimum? Why is 1 bit the minimum? Why do counting systems on computers all just involve zeros and ones? Because you could have current flowing, right? It's either you have electricity there or you don't have electricity there. Or back in the days of vacuum tubes, either the vacuum tube was glowing or it wasn't glowing. You know, a vacuum tube is just a fancy light bulb. Or even before that, you had mechanical arrays. People had mechanical computers before they had vacuum tubes. And so a mechanical array, the relay was either closed, meaning electricity was flowing through the relay, or it was open, meaning no electricity. So that's why we care about zeros and ones. And if you could rip open your computer and look at its RAM, all it would be is a series of zeros and ones, and billions of them if you had gigabytes of RAM. And if you looked at your hard drive, you'd see the same thing. You wouldn't see numbers 0 and 1, though. You know, on a CD-ROM or a DVD, it burns it in the form of pits. And if there's a pit in the aluminum of the CD, then of a certain depth, it means that it's a 1. And if the pit looks differently, it's a 0. And transistors, you know, if the current is one way in the transistor, then it's a 1. If the current is the other way or it's uncharged, it's a 0, whatever. So that's why we keep talking about bits. So something that I want you to remember, 8 bits is a byte. And how many values did we say could fit in a bit? A byte, a maximum is 255. So 1 byte can hold the values 0 to 255, because 8 bits can hold those values, right, from that to that, for possible 256 total values. This will become important in a later lecture. Go to that worksheet. Let's see if we can hit the first part of it. Convert these binary numbers to decimal in the same way we have before. That's 1 times 10 to the 8th. There's nothing there, so I just skipped it. I didn't say 0 times 10 to the 8, 4, plus 1 times 10 to the 2, plus 1 times 10 to the 1, which is equal to 11. Or you could just say 8 plus 2 plus 1 is equal to 11. So do that for the next 4. So these are 4-bit numbers. They can't hold as much as an 8-bit number. They can't go up to 255. Who's got the last one done? What is 1111 equal to? If we were going to add them up, that'd be 8 plus a 4 plus a 2 plus a 1, which is a 15. So 4 bits can hold up to 16 different numbers. 0 all the way out to 15 is 16 different values. That'll also become important in just a little while. So this one, don't just give me the answer, but tell me what the numbers are. It's a 4 plus a 2, which is equal to a 6, obviously. How about that one?
8 plus 4 plus 1.
Right. Now, is everybody getting this? I see several good strong head nods. And lastly, well, that's obviously 0, right? Okay, now to convert backwards from decimal to binary involves a completely different process, and I'm not going to ask y'all to do it. I think I'll demonstrate it if we've got a pen. And you may not even be able to see this. I know that when I raise this and I start writing on the board, some people can't see it. But say we had the number 13. The way you convert backwards is you divide this number by 2. And you get 6. But there was a, what was the remainder, like if we had modulused it? 1. Okay. So now we take that 6 and we divide it by 2. What do we get? 3 with a remainder. So this one, 6 modulus 2, had a remainder of 0. So 2 goes into 3 how many times? 1. And if we did the modulus of that, we had that. And 2 goes into 1 0 times. It's unavoidable. And that's your, you had a modulus of 1 there. So your 13, starting from here and counting up, is equal to 1101. There are other ways to do it as well. Some people do it like this. Okay, I have 4 bits. That's an 8, a 4, and a 2, and a 1. How many 8s can my 13 have? It can have one of them. So 13 minus 8 is 5. Can any 4s fit into it? Yeah, we have a 5, so why don't we pull out a 4? Now we have a 1. Can any 2s fit into 1? Nah. Can any 1s fit into that? Yeah, so we got the same answer doing it that way. But for long numbers, this is actually a more efficient way of doing it than doing it this way. This is the way I think of it actually in my head. How many 16s and how many 32s and how many 64s? But this is just an algorithm, right? An algorithm is something that you can repeat over and over until you get the answer, and this is harder. Conceptually easier. Anyways, so am I going to ask you to go the other way? Am I going to say, okay, what is the number 6,321 in binary? Nah. And you guys who missed the lecture, you also missed looking at the whiteboard. Okay. Okay, now we need to talk about hexadecimal. We've already talked about binary, which we have 0s and 1s. We have 2 possible digits. It's a 2-digit numbering system. And we had decimal, so that was called base 2. Decimal, we had 0 all the way up to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we had 9 digits, or excuse me, 10 digits, counting the 0, so that's base 10. Like I said, computer scientists are crazy about powers of 2. And 10 isn't a power of 2. 16 is. So hexadecimal. Hex meaning 6. Decimal meaning 10. This is base 16. So not only do we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but we got to keep going. That's only 10 digits. And we want 6 more digits. And some of y'all know the answer to this. What did they do to give ourselves 6 more digits? What came after 9?
A,
We had an A and a B and a C and a D and an E and an F, right? That way we had 6 extra digits. Now, if you were Russian, did you use A through F? No, you used different letters. Did they have to choose A through F? No, they could have done I don't know this last 6 letters of the alphabet without looking, but Q, R, S, T, U, V, W, X, Y, and Z, if that happens to be 6. Those could have been the 6 digits. Or they could have used Greek letters, alpha and beta and theta and whatever, But for ease of use, A, B, C, D, E, and F rounded out to give ourselves 16 digits. And the idea may seem weird, but let's hop back in our car, but this is a hexadecimal odometer. So we're driving along. Now we're doing hex. Hex is slang for hexadecimal, even though hex just means 6, but it's easier to say hex, alrighty, than hexadecimal. Alright, have we maxed out our digit counter yet? We actually have not, because we have 16 digits to play with, and we're only here. So we don't roll over yet. Instead, we keep going. We go to the next digit in our counting system. And I know it messes with people's brain to call letter digits. Now we have maxed out our counting system. F is the largest digit in our counting system. So when we need to go to another mile, our digit gets reset back to 0, and we increment the next one by 1. And the ball of wax starts again. And so on, up to 0, 1F, 1E, 1F. Now we've maxed out the F. So what does this become? What does that column become?
0,
Becomes 0, and then this one gets incremented by 1, so it becomes a
2.
2. Yeah. So you keep counting. You get down to, let's say we're at 0B, C, and we're going to keep counting. What comes after 0B, C? What's the, C becomes a
E,
D, which becomes a E, which becomes an F. Now we drive another mile, so this column in our odometer sets back to 0, and this one gets incremented by 1. Add and carry, So what does B become? And so on. So until you hit 0FF, what does that one become? It rolls over to be 0. We add and carry. F can't get any larger, so it resets to 0, and we add and carry, and we're there. All right, I hope that makes sense. I don't know why I'm typing so many dots. So instead of a 8's place, a 4's place, a 2's place, and a 1's place, like we have in binary, which is, 2 to the power of 3, 2 to the power of 2, 2 to the power of 1, 2 to the power of 0. Or, if we were counting in decimal, we'd have 10 to the power of 3. For some reason, I'm having a hard time finding my caret now. 10 to the power of 2, 10 to the power of 1, and 10 to the power of 0. That's our decimal counting system. So that's 1,000, right? That's 100, that's 10, and that's 1. Alrighty, so if decimal has 10 to the power of whatevers, and binary has 2 to the power of whatevers, then what's hex going to have? What is hexadecimal going to have? It's based on how many digits? 16. So it's going to be 16 to the power of 3. 16 to the power of 2. Really? (16 to the power of 1) and 16 to the power of 0. So let's just go ahead and convert those. Any number to the power of 0 is what? I already said this, 1. Any number to the power of 1 is itself. Any power to 2 is you square it, you multiply 16 by 16, and you get 256. And 16 to the power of 3 is, I think it's 4,096. So if you had this number in hex, 1, 2, 3, 4, and I'm going to put parentheses 16 after it to say that it's hex. Another way that people represent that is they put OX 1, 2, 3, 4. You'll see computer scientists do this a lot, and it won't make a lick of sense to you unless you know that this 0x actually means that it's a hexadecimal number. But anyways, so if I say 1, 2, 3, 4 base 10, that means it's a decimal number. If I say 1, 2, 3, 4, 6, parentheses 16, that means it's 1, 2, 3, 4 in hex. And those are completely different numbers. Why is that? Well, let's take our little counters here again. And let's type in a 1 and a 2 and a 3 and a 4. So this is 1 times 4096 plus 2 times 256 plus 3 times 16 plus 4 times 1. And I can't do that in my head, so I'm going to allow Manjari Google to do it again. And there we go, 28676. So 1, 2, 3, 4 in hex, or in base 16, is equal to that. Oh, really? All right. Whatever that thing said it was. Come back, Google. Save me. 28676. In base 10. What if we had 0, 3, A, 9? Okay, and that was in base 16, obviously, because our counting system doesn't have A's in it, decimal doesn't. So we have to kind of remember what the letters mean. In hex, the numbers 0 through 9 mean the same thing as decimal, right? But then we have some extra ones. We have A, B, C, D, E, and F tacked on to give us 16 of them. So an A is a 10, a B is 11, a C is a 12, a D is a 13, an E is a 14, and an F is a 15. So now that I have this number, this means 0 times 4096 plus 3 times 256 times, what did we say that A was? 10. So 10 times 16 plus 9 times 1. And again, I can't do that in my head. So
Multiplication sign. You got 256 times 10.
thank you. I'm not spotting it. That is accurate, right? Because A is 10.
But you don't want the multiplication sign before the 10.
Oh, yeah. Thank you. Thank you, thank you, thank you. All right. I would have wondered why the number came out that large. 937. So this is equal to 937 because those numbers added up is equal to 937. Am I going to make you do that? I don't really think I am. I don't think that's part of the worksheet. However, we do want to be able to convert from binary to hex and hex to binary. Fortunately, that's really easy. You can just set yourself up a table to do these. Now to hold 16 different values, 2 to the power of 4 is 16. So we need 4 bits to hold 16 different values. And I'm just going to count them out like this. And I would like for you to be able to make this table yourself. I'll probably give it to you anytime you need it. Okay, and then we need some more spaces. Counting all the way up to 1111. So that's 1, yeah. Hope I don't make a mistake and have to re-edit these. I did. Oh, I forgot just, great, I have to redo them all. When 0111 clicked over, what should it have become? Should have become 1000 or 1 followed by zeros. So I botched that. Sorry guys, that was more tedious than I had planned.
You got a double 1010.
I sure do. Thank you. All right, so if we were going to add these up, for example, this is a 1 and no 2s plus a 4, so that's a 5. This is a no 1s, a 2 plus a 4, so that's a 6. All right, I'm going to stop adding them because it's pretty easy to do this from here. That's a 0. That's a 1. That's a 2. That's a 3, 4, 5, 6, 7. So we know what this is going to be. This is an 8, a 9, and what did we say a 10 was in hexadecimal? That's a A, and a B, and a C, and a D, and an E, and an F. So each hexadecimal character is represented by 4 bits. And I know that some of you are thinking, why do I need to know this? And it's because if you deal with programming a lot, you do need to understand the zeros and the ones in the hexadecimal. If this is going to be your only programming and then you're going to go on to do something else, you probably won't need it. Except on the exam. Okay, so based on that, we can convert from a series of, I'm just going to put a 10, an 11, and a 12, and a 13, and a 14 here, and a 15 here, just to remind ourselves that that's what those mean. If you have this series of digits, you can convert those to binary really easily just by looking them up. What's an A? An A is a 1010. What's a B? It's a, maybe I shouldn't have taken away my tabs. So a B is a 1011. I'm going to put a space there to make it easier to read. What's a 0? That's the easiest one. What's a 7? All right, only the front row is telling. I'm going to start calling out names. What's a 2? 0010. And lastly, a 1 is that one. That makes sense, guys? It was real easy to convert from that to that. And some people express IP numbers, internet IP addresses, as pairs of hexadecimal digits rather than as 255.128.6, whatever. Also, if you've ever seen RGB colors, if you've ever used a paint program that did RGB colors, RGB stands for red, green, and blue, and each one of those numbers can be from 0 up to 255. So those are perfectly represented by pairs of hexadecimal digits. So you may say, somebody say, okay, I need a shade of blue that is equal to 14B3F2 or whatever. And so your paint programs, the more sophisticated ones, will let you type in a color very specifically by doing a hashtag followed by a series of numbers that represents a color. All right, and we can go backwards. Say we have this. Let's convert those. I'm just going to put equal now. There. To hex. Maybe there's too many of them. No, let's go for it. All right. So what is a 1011 on our little lookup table? It's a B.
Rob.
What's a all ones? What is all zeros followed by 1? That one's easy. It's 1. What about that one, guys? It's a 5. That? Did I do 2 B's in a row? Yeah, I did. Okay, and then lastly, 6. Okay, so now you know how to convert from binary to hexadecimal or from hexadecimal to binary. Why did people even care about hexadecimal? Well, because when you were in the old days of computers and you had very primitive things going on and you needed to convert series of bits into data that you could display on the screen, then you may have thought, okay, I'm going to convert these to decimal numbers. Let's convert this same series of values into their decimal equivalents. Now they're all going to be the same except for the letters. A B is an 11. An F is a 15. A 1 is a 1. A 5 is a 5. A B again is an 11. And then a 6 is a 6. So say we had that. That's not really good enough. If you're reading this, you can't really figure out if this is 11 followed by a 1 followed by a 5, or if it's a 1 followed by an 11 followed by a 5. You have to set it up so that each one takes up 2 digits. 11, 15, that's a 1, right? This is a 5, so we need to make it 0, 5. That's another 11. That's okay, and then we need to do 0, 6. So to display that information on a monitor or in a printout in hex took up this many spaces, 1, 2, 3, 4, 5, 6 spaces on your printout. But to display it in decimal took 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You could fit twice as much data on the screen, which is pretty important if you only had 40 characters on your screen. You know, old computers, you know, didn't have high-res monitors like we have. So hexadecimal was a very nice, clean way of representing bits on screen. And if you're a computer scientist and looked at this long enough, you knew that F was immediately 4 ones and that a B was, you know, whatever. So that's why they invented it, not just to torture y'all, but there was actual practical application as well. So let's go back to our worksheet, and I think we're getting close to done. Convert the following binary series to hex. Fill in the question mark spaces if you're already done. You can use the lookup table. I'll bring it back up on screen, but all zeros is obviously a 0. And all ones is obviously an F. Let's pull up Mr. Lookup Table again, and y'all can do the rest of them. Forget this 10, 11, 12, and 13, and 14, and 15 business. That's not what you want. I may even delete those. sure that some people have done. What is this one? 0110, according to the lookup table. Pardon?
6.
That's a 6. Olivia, what's a 1110?
E.
Is that an E? Alrighty. What's an 0101, guys? That's a 5. The lower ones are pretty easy. You can just add them up in your heads. That's obviously a 1. And going the other way, what did we decide a B was? 1011. And a D was a 7. Everybody say it in unison. 0111. What was an 8? 1,000. What's a 0? I don't know why I put 0 in here so many times. 000. What's an F?
111.
All right. So we're done with our worksheet, I believe. Nope, we're not done with it, but I pretty much call ourselves done. All right, go to the top of page 3. We have 4 more minutes. Converting from binary decimal. So if we have this number, 1010, that's an 8 and no 4s, plus a 2 and no 1s. So that's a 10. Oh, if I've already filled these all in, then that's pretty easy. What do you know? Y'all are saved. These are already all filled in. So this is just the same notes that we've done prettier. Like scroll to this page. Page 9. You'll see our lookup table. And I'll probably cut and paste this into the exam so that when you're taking the exam and I ask you to go from binary to hex or vice versa, you can do it easily. All right, gang. If you got your worksheet filled out, go ahead and save it and upload it. And we will consider ourselves done for the day. I guess I used to actually assign this as homework, which is why it says homework rather than in class. We did it in class. I ought to give you more homework along these lines just to burn it in, but I didn't have any prepared, so let's not. Alrighty, so we will get back and continue on with our chapter on Tuesday.